Bismillahirrahmanirrahim. Assalamu alaikum students. Today we are going to discuss another interesting problem. So let me write the problem. So our today's problem goes like this. It says figure 1 shows a hypothetical closed cylinder of radius r immersed in a uniform electric field E. The cylinder axis being parallel to the field. What is the electric flux, which we denote by phi subscript E, for this closed surface? Let me draw the figure, then we will discuss the solution. We'll draw the first cylinder in some different color. Okay. Okay, this is my figure 1. Let me complete the figure. These equally spaced electric field lines, which are parallel, represent the uniform electric field E. Now, in this uniform electric field is immersed a closed surface of radius capital R. So this is R, radius of the cylinder, and the axis of the cylinder is parallel to the electric field as shown. Now we are supposed, let me check the question first, then I will move. Question says figure 1 shows a hypothetical closed cylinder of radius R immersed in a uniform electric field E. The cylinder axis being parallel to the field. What is the electric flux phi E for this closed surface? So as you know, uniform electric field is, let me write first to the solution. We are moving to solution now. Uniform electric field is represented by equally spaced parallel electric lines of force. These black lines represent uniform electric field E. Now in that electric field, we have a cylindrical surface, closed cylindrical surface with radius capital R. The axis of the cylinder being parallel to the electric field. We are supposed to find the electric flux through this closed surface. Now how we mathematically write the electric flux through a closed surface phi E is written as closed integral E dot dA. I hope you know the meaning of this quantity. You know electric flux is a scalar quantity, and this gives us measure of number of electric lines of force passing through some surface within an electric field, right? Now when the surface is closed, then we have a convention. Well, let me give you a brief uh, introduction to the flux. If there is a closed surface in some field may be uniform or non-uniform. Let me represent these lines representing some electric field. Now in that electric field, we have some closed surface. So how we define the electric field? We divide the surface into infinitesimal area elements and represent each area element by vector dA. The length of the vector is proportional to the area of this patch, but direction is taken as outward normal. This is the convention for closed surfaces. We take the area vector representing the patch of the area outward normal, right? Similarly, here this dA representing the area of this patch is outward normal. Here this dA will be this way. Then what we do, at each patch we find the dot product of the electric flux with the area vector, where E is the, for example, here if we selected this patch, E is the electric field at this location of this patch of the surface. So you find E dot dA for each patch, where dA is the area vector and E is the electric field at the location of the patch. Then we sum these dot products over the whole closed surface, and mathematically that is written as this. So this integral means the electric flux through this closed surface. So what we do, we take a closed surface, separate the surface into infinitesimal area patches, represent each patch by area vector dA. Length of the area vector is proportional to the magnitude of the area, and its direction is taken as outward normal by convention, normal to the surface. So we find flux for each patch as E dot dA. Then we add these dot products of the whole closed surface. If the surface is open, it is not closed, then there will be no circle on the integral. It will be just an integral. But when there is circle on the integral, it means our surface is closed. Now in our problem, our surface is closed, so electric flux is given by this closed integral E dot dA. So let us move to the calculation part. Now what we do, we split the area of the whole closed surface into three portions. We name the area of the left end cap, label it by small a. area of the curved walls we label with B, and area of the right end cap we label with small c, right? So what we do, let me use another color. So the flux, electric flux phi E can be written as the sum of three terms, that is an integral, first part is an integral over A. What is A? The left cylinder cap, the left cylinder cap. Second is B. What is B? The cylindrical surface and third one is C, the right cap. As in the figure you can see, we have labeled, separated the total surface area of this cylinder into three parts. A represents the area of the left end cap, cylindrical cap, B the cylindrical surface, and C the right end cap. So A is left cylindrical cap, B is cylindrical surface, and C is the area of the right cap. Therefore, mathematically what we can do, therefore phi E, the flux to the surface, which is closed integral E dot dA, can be written as E dot dA A plus E dot dA B plus E dot dA C. I'm labeling the integrals as ABC, so they denote the flux through the portions of the cylindrical surface. A denotes the flux through the left hand cap, B through curved walls, and C the right hand cap. Notice we are not placing the circle on these three integrals on the right hand side because they are portions of the closed surface. They themselves are open surfaces, right? Let me show you now in the figure. For left hand cap, let me use some color, I think green. For left hand cap, electric field is to the right. This is electric field, and as you know, area vector is taken to be outward normal, so the area vector is leftward. So you can see angle between electric field and area vector is 180 degrees, as you can see. For right hand cap, electric field is to the right. This is electric field. Area vector is similarly directed. So this is area vector. So angle between area vector and electric field is 0 degrees for right hand cap. What about the curved walls? You can see the electric field for this piece of the curved walls is along the surface, as is true for every piece of the surface. And 8, this is electric field, and area vector is outward normal, dA, angle between electric field and area vector for the curved walls. As you can see, this is theta here, is 90 degree. Here theta is 0 degrees. For this cap, theta is 180 degrees, right? Here 180 degree, here it is theta is 90 degree, here theta is 0 degrees. Now what will happen because of that? For left hand cap, the angle theta for all points is 180 degree, is constant over the surface of the left hand cap, and the vectors dA are all parallel. Thus E dot dA for left hand cap, that is A, is just E dA cos 180 degrees, cos 180 degrees minus 1, and you can take this E outside because E is constant over the whole left hand cap because E is uniform. So what will it become? It will become integral dA cos 180 degrees minus 1. So minus 1 and E I take out of the integral. So what it becomes? It becomes minus EA, where A is, let me write it neatly, where A is pi r square, is the area of the left cap. Capital A is the area of the left cap. So integral dA, when you add all infinitesimal areas over the left hand cap, it will become just A. A is the area of the left cap, which is pi r square, because capital R is the radius of this cap. So this is minus EA is the value of this term. What about the curved walls? That is integral B E dot dA is 0 because cos 90 degree is 0. As you can see, for curved walls or cylindrical wall, theta is 90 degree. So E dot dA is 0 for all points on the cylindrical surface. For B portion cylindrical surface, theta is 90 degrees. So for all patches of the surface, dot product becomes 0. So this integral is 0. So this term is 0. What about the third one? That is integral C E dot dA. As you can see, for this thing, it is plus EA. Why plus EA? For all portions of the right hand cap, E and dA are parallel, theta is 0. So E dot dA is just EDA. Then we take E outside the integral, as we have done in this part. But only one thing here, we have cos 180. In this case, we have cos 0. Cos 0 is 1. It becomes EA. A is the area of the right hand cap. So for right hand cap, we have the flux equal to plus EA. So one term is minus EA, second term is 0, and third term is plus EA. So what is the total flux now through the surface? Therefore, phi E is minus EA plus 0 plus EA. When you add it, it is 0. So flux through the closed surface shown in this figure 1 is 0. So this is our answer. Electric flux through the closed surface shown in the figure 1 is 0. As is expected from Gauss's law, you know electric flux through some closed surface is proportional to, you write this equation, Gauss's law. You know Gauss's law for electrostatics says net flux through a closed surface is equal to Q by epsilon naught, where Q is net charge inside the closed surface, which we call Gauss's surface, Gaussian surface, right? So here you can see inside this surface there is no net charge. Q is 0. So from Gauss's law, the electric flux through this surface must be 0, as we have calculated it. It is in accordance with Gauss's law that this surface contains no net charge, so the flux through this surface must be 0, as we have calculated it. I hope you got this problem. Enjoy all these problems. Don't waste your time. Go through all the problems, make notes out of it, and don't forget to like, share, and subscribe my channel. You can give comment in the comment box. Thank you. God bless you. Assalamu alaikum.